So we are not literally here, but approximately we are in the transition from continuously defined wave functions for harmonic oscillator. And I do have intentions, and since we all are sitting at home much more than in the labs and offices, I have a very good look at the office that I want to maybe scan a couple of pages and share. So at least about the options, what are examples of harmonic oscillators, so that it's the easiest part of this chapter, and it is maybe something that one can take home for years rather than this monthly observations. I will combine leftovers of the individual research projects, and I will do it at the end, like last 15, 20 minutes. And we need to go to energy of ground state. Describe it in the way of more discrete Hamiltonian discrete states. And this is needed because later on you'll go to the excited state dynamics, which is very hard to do in the old-fashioned continuous and much easier in discrete representation. So I didn't get any reminder or I missed the email, but maybe I'll send it on the weekend. The homework just accompanies the class material of making the transition to discrete. I believe we covered it on the previous lecture, so it's basically copy-paste. And the number 3. Oh, I see. Spencer didn't connect it. Say hi to everyone. Oh. Hello, Spencer. Okay. The number 3 is here's the idea. The creation of any equation operators as a proposition of position momentum. And if one takes definition of creation and annihilation and solves it, one can express position momentum as some summation and subtraction of the creation and annihilation. Then from number 1, one would have the matrices for creation and annihilation. And if one follows the rules how to compose position momentum out of those operators, one can just add and subtract matrices. Make sense? Spencer has a question. How are we proceeding this question to where you request a verbal description of the trend? Number 2 is not hard. Like you can verbally describe, like, are the diagonal elements 0 or non-zero? Are they the same or they're growing or ascending? Then use annotation. Then you can go to this upper subdiagonal. Upper subdiagonal. And tell, are they the same or different? Are they ascending or descending if they're not 0? Then one can go to the lower subdiagonal and tell whether are they 0, non-zero, growing, or ascending or descending. So it is just summarizing observation from number 1.
Spencer, I think to answer your question, just describe it in words rather than in equations.
Sure. Thank you. Spencer, are you satisfied with the answer? Okay, good. So maybe we'll skip filling this table to maybe later, next meeting, but I'll continue and hope to complete the list of entertaining stories today. But before we'll go to the things of transition between continuous and discrete. So I want to believe that one day we did arrive to this equation. Do you remember it? So it means that in discrete representation of eigenstates, in the matrix representation, the energy, the Hamiltonian energy operator is has only diagonal elements. All of that, so this ket and bra k and k means that only diagonal elements are not zero. Everything else is zero, and the value of the diagonal element does increase according to the number. And in some sense, this equation on the top is related to the answer to question 1 from the homework. Right? Okay. So there are two goals which I may or may not complete, considering that I need to entertain these possible projects. But the goals are as follows. First one, we need to make ourselves comfortable with this quite trivial result, quite trivial property. And the meaning of this equation is that energy of the lowest state of the harmonic oscillator, whatever it describes, quantized electromagnetic field, oscillating atoms, or something more exotic, the energy of the lowest state is bigger than zero. And the meaning of this equation is the same as in particle in the box. So if you do have confinement, if the walls become smaller, it pushes the energy of the lowest state to be above zero. So if we change curvature of oscillator from shallow to steep, then the energy of the lowest state increases. So it's the same idea as confinement. If there is less space permitted for particle to move, then the lower energy of the lowest state is higher. So, and it's kind of trivial, but we want to discuss it a little bit more so that the Hamiltonian and this basic conclusion, I promise, will be used in the next PCAM class, like routinely several times per each meeting. So the stuff here is really cool thing. The Roy Glauber got Nobel Prize for it. So in some sense, our class is a list of Nobel Prize in physics and chemistry. The equation here is well known to everyone who was attending each meeting here. You did solve this equation, but by looking on it, you may not recognize it. So maybe let's give me a second to this and ask you guys to share opinions. What do you observe and how do you interpret this this equation?
The eigenvalue equals the operator.
Yes. So it's eigenvalue problem for which operator?
of annihilation.
Yes. What is the eigenvalue of the annihilation operator? Please give at least one eigenstate of the annihilation operator. Try to, and
Square root of 2.
think about Stroman. Look at this earlier in the note.
Number of states, density of states.
When we just started harmonic oscillator later, so about here.
Square root of
Those are ways to express annihilation operator as differential operator. Maybe flip the page to 5. Yes. So how do you arrive to? No, it's phi 1. Is there a phi naught? Is there a phi naught in your notes?
Oh yeah, it's a square root of MW h bar pi e to the minus MW over 2h bar r squared.
Good. So how did we arrive to this eigenstate?
And not the position operator.
We remember about Stroman trying to go lower than the lowest state.
Oh, where we plugged in all the values below 0 and came up with the value of 0.
Exactly. Now I need to insert a free page, and I think it is more valuable than just.
You can hit Control M.
Control M to insert new page.
Yeah.
I'll try. In the presentation mode or only in the editing mode?
If you just click Control M, you'll get another slide.
Oh, excellent, thank you. I don't know about you guys, but I'm learning something new from this class. So A acting on psi naught was 0. Now on one side. On another side, we have A acting on unknown function equals to eigenvalue. So if we assume that there is a function which provides eigenvalue alpha equals 0, then it will read A phi equals 0. Does it look similar? Yes. So if we hypothetically assume that there is an eigenstate of annihilation operator with eigenvalue 0, then we have already found it, right? So now I am going back to here. So if I will plug mu equals 0 and solve this equation, it should give the ground state. And we can prove it. But if we set up that mu is unknown, it will be something more advanced. We do not know yet. Why do we need this concept? This is the hardest question to verbalize and explain. I have very clear mind, but I have very unclear words to tell, or disorganized. If we consider the probing of the interatomic distance, interatomic bond by electromagnetic wave, what are the typical frequencies for oscillations, for bond length oscillations. Typically, they're measured in inverse centimeters.
Sine and cosine?
No. Numbers. Like, I don't know, maybe I'm too optimistic about your labs and in-lab experience, but I want you to answer FTIR. Signal frequency in inverse centimeters. 1,500 is a carbon-carbon stretch. 3,000 something, it will be CH stretch. Does it tell anything to you?
Looks like IR.
Exactly. Yes. Yes. IR, and it's just one of the versions of the FTIR. So tell me more about that. I do not have experience in wet labs, so you can teach me what are those.
Absorption?
Yes, in which frequency range? Like in infrared, is it shorter or longer wavelengths? Is it larger or bigger energy compared to visible?
It's smaller than
Super, smaller than visible. So if you want to probe oscillations of interatomic distances, we may want to excite it with a laser of the frequency below the visible range, in the infrared region. So what would happen to like a polar molecule which has a dipole and will respond to electric field if we irradiate it at the resonance frequency? It will launch amplitude of oscillations. Originally it will be as good as zero, very close to zero, and then it will start ramping with more and more intense. So one way to think about this experiment is that we do have like ball in the spring, which is a classical particle with specific position, and it just increases amplitude. But we do know that if the ions are really small, like protons, they are distributed with probability, same as electrons. And we want to translate this concept of increasing amplitude after irradiating by laser onto the language of quantum states. How would the distribution of probability in space change over time? Or how would the occupation of eigenstates, if you already know them, change with time if we ramp up our interatomic, our bond with the laser?
Would it get bigger?
Yes, I share this intuitive vision. It should get bigger. It should become more distributed. But luckily for us, there is a way to address it even without computers. It's one of the problems that does have pen and paper solution. And the equation that we are looking at is our bridge to this describe the situation. So it will describe the situation if the interatomic distance has been excited by laser light in a resonance, so that it will be analogous to increased amplitude of oscillations in classical representation. So the idea is very basic. Wave function is represented as an expansion over eigenstates, summation of all eigenstates with unknown coefficients. And the operator will be represented as the matrix, as we've seen before. And then we hope that there will be a way to solve, to find each C sub n and find mu. Whew. I do not hope to do it today, but we need to push our efforts through the course. So I'll go forward this slides. So here is the energy operator. If we plot it, under MATLAB, it will be like skyscrapers in the center along the Broadway in a big city, or the height will increase bigger and bigger. So something about sandwich. It's not about food, it's about the way to extract observables out of wave functions. You put an operator of observable as a sandwich between two wave functions, and then integrate. So if we are on the way from continuous distribution to discrete stuff, then our psi naught should be just ground state occupied with one, all others are empty. And our Hamiltonian should be this matrix with skyscrapers growing from 0 to the end. So we are going to just make this little practice and make sure that we know the answer, but we need to practice and make ourselves confident with this sandwich procedure so that we can do it better in more complicated situations. So the total energy operator is this summation of ket and bra. Anytime we see a constant in the operators, we should understand that constant is multiplied by unity operator, which is matrix with ones on the main diagonal. And then for our matrix element, we multiply it from the left and right by principle of sandwich. And then we do practice the orthogonality and orthonormality principle. Let me check if I was typing it nicer. Yes, I did. I'm grateful to myself. So here is the Hamiltonian. Here is bra for ground state. Here is a ket for ground state. And we are going to put it inside the brackets. Here, this will go there, which means 0 overlapped with k, bra 0 k will be non-zero only if k equals 0, right? And another term, bra k ket 0 will be non-zero also if k is non-equal 0, if equals 0. So here k equals 0 means this term disappears, and here if you're looking for element number 1, we still keep this 1/2. And we do have factor of frequency at the front. So as a result, we'll get h bar omega times 1/2. Make sense? Yeah. So it is trivial, but if you get something more complicated, we should follow the same procedure and same logic. And it is very quick and efficient, much quicker than any other way to process operators or matrices. Okay, first goal is accomplished. Okay. So it is what I was telling. 0k, k0, 2 delta functions, perform summation, delta functions and summation disappear, k disappear, 1/2 stays. First goal is achieved. So on the way to finding eigenstates of the annihilation operator. It's very powerful stuff that allows to describe, as we discussed, laser acting on this bond. It can describe the laser itself. It can describe anything where quantized oscillations are present. And it's, in some sense, we are doing, I saw it in one of the fiction medieval movies where one needs to conquer a castle. One takes an anchor, throws it, and tries to climb. So this eigenstate of the annihilation operator is our anchor that you later allow to describe truly broad range of phenomena. So even without describing what it is, I just ask you to believe that it is really, really helpful thing. Also on the a little bit less helpful than Schrödinger equation itself, but on same. Okay, it looks like I am permitting myself to relax, or to you to relax, and me to entertain you guys. So one of the main goals of the course is to apply your skills and knowledge to realistic things. By the way, you're very, very welcome to watch recordings and reports of the previous years. In real life research, one cannot sell the same research twice. It's called plagiarism. So, but standing on the shoulders of giants or just predecessors from previous years is very healthy. If you can copy paste something from there, it's not cheating. It's a true scientific process where you just borrow inspiration, because your problems will be new and different from them and from each other, and anything you can borrow from other sources is helpful. So do not hesitate to read and check what it is. Each question will be unique. So there are purely electronic, purely nuclear, mixture between electron and nuclear, spin and angular momentum, and some additional chapters. In here you do see model and ab initio. Model, ab initio, model, ab initio. What does it mean? No, and did you want to ask me or you don't care?
I wanted to ask if we have to do both.
Yes, but time is limited, and I'm very happy if you want to do both. But first, we need to do something in a very short time before the course ends. So model means we just do some formula or just piecewise design of the potentials where your electron or nucleus is moving. And ab initio means that a graduate student or a postdoc will run ab initio calculation and share with you the potential, which will be more fundamental and related to the real system. Okay, so if we are looking on the model, then a dip in a potential is where ions are placed. Bless you, bless you, bless you. Where are different several ions and different depths of this hump means it is interface between two materials, like donor and acceptor layers in the solar cell. If there is a material and then nothing, it means material is exposed to the vacuum. If overall slope is added, it means it is external electric field, either like photodiode, solar cell, or electrochemistry experiments. If there is only very few of different lengths, it is not a human finger. It is like dye-sensitized solar cell, where dye and semiconductor interface and can exchange electrons. Sometimes one steps out of the building in the middle of the night. And if there are no clouds, some people enjoy observing stars. If one uses telescopes, one can get more exciting images. And if there are very big intensity, very distant stars, one telescope could be insufficient. One may use 2 telescopes. I'm not kidding, I'm not joking. It is much more than just using to double their strengths. It is, in principle, very different effect. So, if a star is very far from us, the detectors, cameras that we add to the telescope, the focus of the telescope, will catch not just infinite number of photons, but few of them, sometimes even single photons. And if one wants to look in the sky in the city, especially in the big city, but probably would count as a big city, one would not see very much because there is a background noise of the light reflected from the air coming back into the telescope. And one does need to discriminate the good signal from a real star from noise signal reflected from the air. And if one uses 2 telescopes, there is a way to do it. So it is not new for this year. It was used like half a century by Henry Brown and Quiz. So if they did a little railway with 2 telescopes, and they look if the signal on 2 telescopes is identical, it means it is from the star. If it is different, it means one of them got this noise photo. And this idea very soon was borrowed from astronomy to micro science, nanoscience, so laser science. So if we want to make our computers much more powerful, if you follow the science-related news, there is a concept of quantum computers, right? Which uses quantum properties of excited states. And in order to practice those quantum computers, one needs to, for quantum computers, one needs a quantum, single quantum. So one needs a meter of single photon. And in order to discriminate single photon from multiple stream of photons, one uses the same concept for 2 telescopes. Of course, it is not a telescope if it is a micro world. One needs a micro detectors. But the idea is the same. If the signal in 2 detectors is correlated or not, it will be something good or bad. And one of the materials that can potentially create such photons is carbon nanotube with a boot. Carbon nanotubes itself do not emit light, but with absorbing they do.
Good.
Depending on how this adduct is attached to the surface of nanotube, they emit slightly different frequency. And there is a technological question, how to create homogeneous emitter. So those are isomers. Chemically, they are identical, but by their properties, optical properties, they are different. So just relative position of where this mushroom is growing and where this little hydrogen is present. And there is a way to control where they are sitting. Sound. So if the molecule is irradiated by light, then it let hydrogen to depart from the molecule. It sticks there, and then the radical comes back. So this reaction can be controlled by either frequency and intensity of the irradiating light for the photochemistry reaction, or by presence and absence of oxygen. A little research project is that depending on the presence or absence of oxygen and parameters of the light, the defect is forming in different isomers, and they are different by the profile of energy and by the intermediate in the middle of the reaction. So the project that one of the class attendees may select is either to look on the reaction itself, how the packet comes through the potential and gets to one of the product, or so if we take the reaction in the middle and look on the intermediate, then the intermediate for different pathway creating different defects will be chemically different, and they will allow or permit different patterns of the charge transfer between nanotube and contact, which leads to different distribution of charge and spin around this components of the reaction. So the stuff that can be done is to extract potential corresponding to electron transfer between nanotube and the thing, and explore wave packet dynamics transfer between nanotube and duct as a function of potential. Okay, then junctions and interfaces, which gives opens the door for photovoltaics. So I know that some of you are working on conjugated polymers that help to do either light emitting diodes or photovoltaic cells. Alternative and more traditional way is to make interface between solid semiconductors, and there is a hybrid way where one part of the interface is solid, another is organic dye, like Dyson's dies or cells. And one can extract the potential that electron is experiencing while moving from the semiconductor to the, let's say, Hall acceptor, and explore motion of electron in this potential. So here in class we can do only one-dimensional problems, but one of the former class attendees continued it and did it more advanced two-dimensional. So here is the model. Points are atoms.
The colors are axis colored gold and colored itself. So initially, orange and blue are localized on the square for the semiconductor. As time passes by, blue stays for the semiconductor, and electron is transferred to the acceptor, which is taken into the and most of the electrons are targeted to titanium 3D orbitals.
Angular momentum. This subject was selected as possible research direction almost every year for us. Of course, we cannot do the same thing every year. Some of you who is looking for, I don't know, unfortunately, I didn't take personal interview from all class attendees, but maybe some of you have plans of teaching career. And this illustration of Bohr model is very appropriate. So what was done in previous years is to explore concept of eigenstates, like if one sets up the non-integer number of angular momentum, would the state be a stationary? So solving finding eigenstates in trial way, same as we did in the last lab for harmonic oscillator. It is done, but it is just an idea. Another thing, one was looking how the eigenstates in this Bohr model, in this rotation, change in presence of magnetic field. Basically, they should rotate clockwise and counterclockwise. And some of the previous found it fun. So if the number of quanta is even, this eigenstate is the same, it just slightly shifts, but it's a shape. And if it is odd, it's something ugly that definitely is not stationary, is decomposing this time. So, continuation. Another project, personal project, that was done only once in previous year, and maybe it is the most challenging. If you are not looking for big challenges and research career, probably just bring back and skip it. I just bring it to your attention, just in case. So, it will be about Dirac cones, like peaks of the less ones. But before, here is the context. Again, modern civilization is looking to speed up computers into quantum computers. And one of the candidates to carry the qubits is two-dimensional materials. The best example is graphene, and there are some other, like molybdenum disulfide, bismuth telluride, and some perovskites, where electrons are allowed to move in one plane and cannot escape. Basically, it's two-dimensional materials. When we looked, when we were looking at the pizza box, when we were looking at the particle in the multi-dimensional boxes. So, if the electron is experiencing such confinement, then the occupied unoccupied electronic state will be in between metal and semiconductor. The criteria of material being called metal, semiconductor, or insulator is the energy of set between homology, occupied and unoccupied. When it is zero, it's typically metal. But here it is zero, but it is not metal because there is almost no state. Density of states is zero, although the gap is also zero. And if though such materials are exposed to magnetic field, they show interesting properties. So when a loop with current is placed into magnetic field, the energy is changed up or down depending on the direction of the current. And this is one of the principles used in the NMR, right? In magnetic field, the levels are split. If one applies such stuff to this two-dimensional material, their density of states segregates onto individual states rather than continuous. So density of states was more continuous, now it experiences more isolated states. And those isolated states are really good candidates for carry quantum information, transitions between such states. So it is a challenge because magnetic field is not typically included into the modeling. So here one needs to include magnetic field, and one stuff done here was to explore eigenstates and to see how the motion of the wave packet is happening in 2 dimensions. This very mind-throwing aspect that here the motion is not in the real space but in momentum space that we slightly covered in describing the methods. And if one applies it not to the graphene but to this bismuth telluride, there is an interesting feature which is probably the most promising. The cone with zero density of states and zero gap is only one, while in other materials there are several cones, and it is not compatible. In this material, there is only one cone for this density of states, and one can look at this cone from different aspects, place it into the method, and explore how with the wave packet moving this dimensions with relation to quantum computing. Meeting is done. Have a nice weekend. Please start making your mind about possible projects you want to explore, and looking forward to see you on Monday.